Welcome back. Have you ever wondered what happens when you press Simulate on your computer? In this video we will discuss the linear solver, which is the heart of many simulators. We will explain the working of direct and iterative solvers and discuss the need for iterative solvers. But first, let's take a look at what problem we are solving. On the right we have a model of the Dutch power network. This model has generator units, loads, and transmission lines. We have already seen that we can simulate this network with different types of models. But in both cases, the main goal is to find a solution that satisfies the power balance at each node in the system. Here you can see a simplified version of that system with only 2 nodes. This system has 4 equations with 4 unknowns. If you look closely, you can see that these equations are nonlinear. For example, the unknown V1 is multiplied by itself. And then there are also unknowns inside the sinusoidal functions. Such a problem requires an iterative solver to give a good answer within a reasonable amount of time. The go-to method is the so-called Newton-Raphson method. This method uses the property that the voltages are related to the active and reactive powers in the system. We are looking for the change in the voltage magnitudes V and angles delta. These are given by the change in P and Q multiplied by the Jacobian matrix. By repeating this computation multiple times, we can get a better and better approximation. We start by guessing the voltages. Then we solve the power balance equation for delta P and delta Q, giving these voltages. This will give the first approximation. Because the system is nonlinear, we will linearize it first around the found powers. Afterwards, we can solve the changes in voltages. Finally, we can update the voltages by adding the previously found change. This process is iterated a couple of times, and during this, the solution improves. A stopping criterion is needed to check when the solution is considered to be good enough. Solving for the bus voltage magnitudes and angles is where the linear solver comes into play. That is also why it's called the engine of the simulators. First, we have the model of the energy system. That model is solved by the Newton-Raphson method, and inside this method we need to solve this linear system. If this is done efficiently, large systems can be solved. Otherwise, it will even take an eternity to solve the representation of a single household. There are 2 types of linear solvers. The first one is a direct solver. The equations go directly into the model. Then that model is solved and we get a solution. The second one is the iterative solver. In contrast to the direct solver, we are not done after solving the model once, but we iterate until the solution is good enough. Only then the solution is returned. Now let us look at both types of solvers in more detail. The direct solver uses the elimination of variables to solve the system. Firstly, one variable is eliminated from all the equations. Secondly, that variable is used and put into other equations. Thirdly, these steps are repeated until we have only one unknown. Then we can solve for this unknown, and finally we can go back and solve for the other unknowns as well. We call it a direct solver because we know beforehand what to do to get a solution. The simple system of 4 equations with 4 unknowns will be solved as follows. First, one variable is eliminated, for instance V1. This is then put in the other equations. We repeat this for V2 and delta 1, and we end up with only one variable, delta 2. We can solve for this variable and compute the rest. There are some issues though. If you have more complex problems, say 1 to 10 million equations and unknowns, you cannot solve them with direct solvers. You could solve it, but it will take a lot of time. Think of a couple of days on a supercomputer. And that is if you are the only user utilizing it. That happens because in the future we have to couple the infrastructures. This is not only for electricity, but also for gas and heat networks. If we use direct solution methods, it is too expensive to solve those models. It simply takes too much time to do the simulation. Therefore, we have to go to iterative solvers. The Jacobi method is an iterative solver and works as follows. First, we put a system in the basic form of Ax is equal to b. We want to solve for x, while matrix A and vector b are known. Then we compose matrix A into a diagonal matrix AD and the rest ALU. Now we start to solve the system. For this we guess an initial solution x. After that we compute the next solution using this equation. Thereafter we compute the error. Finally we repeat steps 4 and 5 until the error is small enough. That means that the solution found for x is accurate enough. Now let's see an example using only 2 of the 4 equations seen before. This happens if we neglect the reactive power in the system. Step 1. Put the system in the basic form. Here the A matrix is the Jacobian matrix, and we solve for delta given P. In step 2, we take the Jacobian matrix and decompose it. Then we perform steps 3 to 6. We compute delta using this equation and repeat this process until the error is small enough. There are several advantages of the iterative solvers. Firstly, they are easy to verify because the computations are cheap with them. Secondly, we have small memory requirements in the computer, which means that they can be implemented on various devices at a reduced cost. So you don't need a supercomputer to simulate, but a decent desktop PC suffices. Thirdly, these solvers can be very fast. For smaller problems, other methods might be faster. However, for large, complex problems, such as the ones we have with integrated energy networks, iterative solvers are the preferred method to use. For both the Newton-Raphson option and the iterative solvers, it is crucial to know the topology and network structure. These include aspects such as, is there a physical connection or not? How is the coupling between electricity, so between AC and DC? And how is the coupling with the gas or the heat? What elements are essential? If you have a vital connection, please keep that in your solver. In contrast, if the particular part is trivial, it can be removed from the computation or evaluated later. Taking all these things into account can help to speed up computations because it can lead to sparse matrices or other valuable properties. By exploiting these efficient solvers can be realized. There are several challenges for solvers. The first one is to find a good starting solution. Sometimes it is easy to find a starting solution, other times we can only start with the zero solution. However, it would help to have a better guess, especially if that guess is close to the solution. The second challenge is how to link the different models and how does that influence the iterative solvers. The answer also depends on whether we have a coupled or a decoupled solver and is dependent on the specific application. The third challenge is what stopping criterion to choose. When is it that the solution considered accurate enough? This also depends on the use case, but popular methods include using a fixed number of iterations or stopping when the solution hardly changes. Let us summarize. We have seen that the power flow problem is solved using the Newton-Raphson method. This method uses a linear solver, which can be both a direct solver or an iterative solver. We have elaborated on some advantages of iterative solvers compared to direct solvers, mainly their faster speed and smaller memory requirements. It's also essential to consider the network structure, leading to interesting properties such as sparsity, potentially speeding up the solver. And finally, we have discussed 3 challenges of solvers: choosing the initial guess, linking the models, and choosing the stopping criterion. See you in the following video.